So in this video, we will first prove that the lead derivative of a vector field W with respect to a vector field V is equal to the commutator of the two fields. Then we will prove that the lead derivative of a function is equal to the action of the vector field on the function. We will compute the lead derivative of a one-form field with respect to a vector field. And finally, we will discuss the geometric interpretation of the lead derivative and connect it to the geometric interpretation of the commutator. So let's review some basic facts about vectors and vector fields so that we can set up the notation. We have, first of all, a curve on a manifold M, which is a map from the real numbers onto M, such that the value of the parameter t of the curve is mapped to a point P, denoted by gamma of t. Then a function on M takes any point on the manifold M, and of course the points on the curve gamma as well, to a real number f of p. We will denote by f of t the values of the function f on the curve, which can be obtained by taking the composition of the curve gamma with the function f. Then the directional derivative of f with respect to t is computed by differentiating this function of t. A special function is the one that takes a point P to a specific coordinate x mu. So let's say that we have a chart chi that so that the P has coordinates x mu, and chi mu takes the point P to the given coordinate x mu at the point P. Also, when we write x mu of t, we will denote the image of the curve gamma on M to a curve here on Rn. And this curve in Rn can be obtained by composing the function gamma with the function chi that defines the chart. A vector at the point P can be thought of as acting on any function on M and giving us a real number, such that a function f is mapped to its directional derivative at the point P. Then, a vector field is a vector defined at every point of the manifold M, and we see that the action of the vector field on a function will give us the directional derivative of f at any point of the manifold M, which is equal to the directional derivative here along an integral curve of the vector field V. So you see this is an integral curve, and one can take the directional derivative of f along this curve. Integral curves of vector fields form a congruence of curves. They fill M and they don't cross. Every point on the manifold M has one and only one such curve going through it. The directional derivative of f with respect to t can be computed in the following way as well. As we have already said, this derivative is computed by differentiating with respect to t this function, but this function can be thought as the composition of those two functions. The first one being the one mapping the parameter t of the curve to the coordinates of the point P, and then this function taking us from the coordinates of the point P to the value of the function at the point P. So, by using the chain rule for derivatives, we obtain this relation here. Therefore, when v acts on any function f, we obtain this relation here. Okay, this is the same as this one. And from here we can read off the components of the vector v in the coordinate basis d mu. So in this basis, the coordinates v mu are just the directional derivatives of x mu with respect to t. In particular, if we choose the function f to be the one that gives us the mu coordinate of the point P for fixed mu, then when v acts on this function, it gives us this, but the derivative of x mu with respect to dx nu is a delta Kronecker, so the action on this function just gives us the component of the vector v in this basis. Now let's see and what is the exponential function. This will shift values of the function f from one point to the other in a specific way. So let's consider again the curve gamma that we discussed before. So let's say that at the point t we have, at the value of the parameter t we have the point P, and at a shifted value of t, call it t plus epsilon, we have the point Q. So these 2 points are mapped via f to 2 real numbers, f to t and f to t plus epsilon. We can use ordinary Taylor expansion to relate this value to this series, and we can write each term in the Taylor expansion in a geometric form by considering the action of the vector v on the function f. So the first term, linear in epsilon, is the action of v on f, and the second term here is the action of v on f, giving us a different function on m, and then acting with v on that function. Similarly, high-order terms are defined by multiple actions of the vector v on the function f. So this reminds us the expansion of the exponential, so we call this the exponential operator e to the epsilon v, acting on f of t. Now, for this definition, it's not enough to have a vector. We need a vector field. If you consider a particular point on the curve, the point P, then f of q, the f of t plus epsilon, and f of p, which is f of t, are related with this Taylor expansion. Now these derivatives are computed at the point P. The first derivative, of course, is the action of the vector v, which is the value of the vector field at the point P. The second term here involves a second derivative, and in order to compute it, we of course act with v of p, but we now have to act on a function. And in order to have a function v of f, we need the vector field at least in the neighborhood of p. So, if we consider the coordinates of the points along the curve, x mu at the point t plus epsilon, that means x mu at the point q, can also be expanded in a similar way. And of course, from here we can read off the fact that dx mu by dt is the component of v in the coordinate basis at the point x nu. So, if x nu are known functions, if the components are known functions of x nu, and the values of these functions are known at a given point of a curve, then this equation here has a unique solution. And this solution is what gives us the integral curves of V along the curve. The uniqueness of the solution implies that integral curves never cross, because at each point there is one and only one integral curve that if we start at the point P, we have a unique one going away, therefore we cannot have two curves emanating from one point P. So let's choose now a coordinate system and the corresponding coordinate basis, d mu. Then the vector fields can be written as a linear combination of the vectors of this coordinate basis, where the components are given by those derivatives. And those derivatives are directional derivatives along the integral curves of the vector fields V and W respectively. In that case, we can define a new vector field which we call the Lie bracket of V of W. And this vector field is defined by its action on any function f on M. So the result of this action are two terms. The first one is obtained by first acting with W on f, and the function that is obtained after this action is acted upon V. The second term is obtained the same way but in the opposite way. Note that in order to define the commutator of two vector fields, it's not enough to have vectors at a given point, but we need to have vector fields, because we see here that the vector fields act on functions that are obtained by the action of a vector field. So in order to have such a commutator, the vector fields have to be defined at least in a neighborhood of the point P. So let's see what this definition gives us if we consider the components of those vectors in the chosen coordinate basis. So when W acts on F, it gives us this function here. And when V acts on this function, we obtain this term. Similarly for the second term. Then we can apply the Leibniz rule for the derivative d mu and have those two terms for each term. But because the partial derivatives commute, those terms cancel out, and if we take d nu f as a common factor, the common factor is this one. And this is nothing but the expansion of this vector in the coordinate basis d nu. So this is actually the new component of the commutator B with W. Therefore, the mu component of the commutator B with W is obtained from this equation, which is easy to memorize because what we write is V times W, and then the opposite way, like in any commutator, minus W times V. We put the partial derivative in the middle, we contract with the vector on the left, and then we are left over with the index of the component of the commutator. Let's now compute the Lie derivative of the vector field W with respect to the vector field V. So let's consider the vector field V, and this is its integral curve that defines the one parameter family of diffeomorphisms phi of t. So a point P is dragged to a point Q under this map to phi t of p. Then let's consider a chart that contains a neighborhood that has both P and Q inside it. Then the point P under this chart has coordinates x mu of P, and the point Q has coordinates x mu of Q. Then consider a small enough neighborhood of P that does not contain Q anymore, such that when this small neighborhood is mapped with phi t to a neighborhood of Q, these two neighborhoods are disjoint and have no common points. Then the restriction of the chart on those two neighborhoods will give us a restricted chart around the point P and the point Q. So we will use the notation that the coordinates of the point P are x mu of 0, 0 denoting the fact that P is phi 0 of P, and x mu of t are the coordinates of the point Q, taken from the fact that Q is phi t of P. Now, let's consider a vector field W. A vector field W has value WP at the point P and WQ at the point Q. Since phi t is a diffeomorphism, we can pull back the vector WQ to the point P. The components of this vector here are related to the components of WQ with this well-known relation. Now, let's consider the coordinates of the point Q. These are related to the coordinates of the point, the coordinates of the point P. These are related to the coordinates of the point Q by applying this exponential operator with minus t here to drag it back to the point P. So this first order is given by x mu at the point Q plus the value of this derivative at the point Q. But this is nothing but the action of, this is nothing but the component of the vector field V that defines the one-parameter family of diffeomorphisms, phi of t. So this defines the values of these functions in the neighborhood of x mu of 0 and in the neighborhood of the point Q. So this is a mental exercise because this does not make any sense mathematically. But if you take the derivative of those coordinates as mapped by phi of t to this neighborhood of Rn with respect to the coordinates here, then what you will find from this relation is that this derivative is delta nu mu plus the derivative of v mu with respect to d nu. And then we ignore higher order terms of order t square and higher. Then we can substitute this in equation 1. So we take this and we plug it in here and we obtain this equation. So by doing the algebra, the first term is the component W mu at the point Q, and then minus t, the derivative of mu, or derivative of mu with respect to dx nu at the point t, times W nu of t plus terms of order t squared and higher. But the component W mu at the point t can be expanded in a Taylor series and obtain this relation up to terms of order t squared. And then this derivative here with respect to t can be obtained by using the chain rule of the derivatives here. But dx nu by dt at the point P is nothing but the component of v nu at the point P. Similarly, the value of this derivative here at the point Q is the value at the point P plus terms of higher order. Substituting this to equation 3 here, we obtain that this component here is equal to this expression, and if we keep terms up to order t and ignore higher order terms, we see that this component of the pullback vector is given by the component of w at the point P plus this term here. If I divide by t, then I obtain this term here plus corrections of order t. Then, if I take the limit t going to 0, these terms vanish, and I obtain just the new component of the commutator of v and w. Since this is valid at any point P of the manifold M, this is a relation that holds for the vector field LPW. Now let's compute the Lie derivative of the function f. So again, we have the vector field v that we have here with respect to which we differentiate. It defines the one parameter family of diffeomorphisms that maps the point P to the point Q. So P is dragged to Q by phi of t. So if we take any function f, whose value is f of p at the point P and f of q at the point Q, this can be seen that it is equal to the pullback of f at the point P. So the definition of the Lie derivative is shown here, and it involves the pullback of f at the point P. But we have already shown that this is equal to f of q. Now, if we consider the integral curve of v going through P as a curve gamma, then v of P is the operator d by dt. And when it acts on a function f, it gives us this derivative here, and we see that this term is f of q and this term is f of p. So comparing equation 1 and equation 2, we show that the Lie derivative of f with respect to v is equal to the action of v on f, which is the directional derivative of f with respect to t. So let's go on by computing the Lie derivative of a one-form field omega with respect to a vector field v. What we will show is that this Leibniz-like rule holds, where when the Lie derivative acts on the function obtained by the contraction of omega with w, this is equal to the contraction of the Lie derivative of omega with respect to v and w, and the contraction of omega with the Lie derivative of w with respect to v. And we have already seen that this relation is useful for computing the Lie derivative of omega, because the left-hand side is shown, because it involves the Lie derivative of a function, and we know how to compute. And this involves the action of one form on this vector field, which we already know that it is equal to the commutator of v and w. And you see how we used this relation to compute the components of the Lie derivative of omega in the previous video. So the definition of the Lie derivative of omega with respect to v at the point P is given by this relation here. So what we actually have to do is to consider again the one-parameter family of diffeomorphisms defined by the integral curves of the vector field v, under which the point P is mapped to the point Q. Then we can use pullbacks to move, let's say, the vector Wt, which is the value of the vector field W at the point Q, back to the point P, or vice versa. And if we have the one form omega t, which is the value of the one form field omega at the point Q, this can be pulled back to the point P and obtain the one form phi star omega. Then this can be compared to the value of the field omega 0 at the point P, and this way we can take the difference and compute the derivative. So using the definition of the pullback of the one form, we can compute the first term by taking the action of omega at Q to the pushed forward vector phi star W from the point P to the point Q. Then we add and subtract the same term here. And by using the linearity of the action of omega on vector fields, we can form this first term here, where omega is acting in this linear combination of those two vectors. The second term here is simply given by this term. So when we take the limit t going to 0, the second term here will give us the Lie derivative of this function. We also use the trivial fact that because of the continuity of the one parameter family of diffeomorphisms and the one form omega, then this limit is equal to omega 0. Then the vector that omega acts upon, as t is taken to 0, we see that it is approaching the value of the derivative of w, but now in the minus v direction, because here you see we have the pullback under phi to the minus t. And of course it is easy to see that the Lie derivative with respect to minus v is equal to minus the Lie derivative with respect to v. Therefore, we arrive at this relation where the Lie derivative of omega acting on w at the point P is minus the action of omega on LV w, plus the Lie derivative of the function omega of v at the point P. Rearranging these terms, and because this relation is holding at every point P of M, we arrive at the desired relation. So now let's move on and discuss the geometric interpretation of the relation that connects the Lie derivative of W with respect to V and the commutator of V with W. Let's consider first the commutator of V and W. We start by assuming that we have two vector fields V and W, and each vector field has its own integral curves. V has integral curves, the T lines shown in this diagram here, and W has the lambda lines as its integral curves. And along those curves, one parameter family of diffeomorphisms are defined: phi of t for V and chi of lambda for W. So let's do the following two walks starting from the point P. First, we move on to the right. We move from the point P to the point Q. The point Q is the dragging of P along phi of t by parameter t. Then from Q, we move along a lambda curve and arrive at the point T. Then we walk from the point P to the left by first walking on a lambda curve, arriving at the point R, and then riding on a T curve to the point S. What we will show is that if this walking is done by equal parameters, lambda and t are equal to epsilon, then the difference of the values of any function f at the point t and the point s is not 0, but to order epsilon square is given by the commutator of V and W. So we see that this walk leads us to different points S and T unless V and W commute. So if they don't commute, these points S and T are distinct. We can see that by applying this relation to the mu coordinate of the points T and S, and we see that those differ by the mu component of the commutator V and W. So let's compute this relation. As we have already said, Q is dragged along phi of t from the point P. Sorry, P is dragged along phi of t to the point Q. And then the point Q is dragged along chi lambda to the point T. Then the point P is dragged to R using chi lambda, and R is dragged to the point S using phi t. Therefore, if we take any function f, its value at the point S can be obtained by starting from its value at P, use the exponential operator e to the lambda wp, arriving to the value of the function at the point R, and then use the exponential operator e to the tvr to move from R to S. So let's consider first this term. Now, by acting with this operator, we obtain a series which we will terminate to order t squared, f of r plus t, the action of v on f at the point R, plus order t squared, two actions of v. First v is acting on f, we obtain a function, and then we act with the vector v at the point r to obtain a number. Then we have higher order terms which we ignore. We can also write this relation into a more familiar form that resembles a Taylor expansion. F of r can also be expanded by acting with exponential operator e to the lambda wp. That will give us again f of p plus lambda wp acting on f plus lambda square over 2. W of f gives us a new function, and acting with the vector wp we obtain a number plus terms of lambda cubed and higher which we ignore. The second term here can also be expanded. We know that this is the value of the function df dt at the point r. Okay, so we have to take the derivative along this direction and evaluate it at the point r. Okay, so the derivative is along this direction and take the number at the point r. So this is also a function in the neighborhood of r and can be obtained by the value of the derivative at the point p acted upon this exponential operator. So we can have an expansion in series starting with the value of the derivative at the point p, then wp acting on df dt plus terms of order lambda square and higher, which we don't need because this is multiplied by t. So the first term here is the action of vp on f, and this term here is the action of wp on the function v of f. Then this term here is this function, d squared f over dt squared, evaluated at the point r. So if this is considered a function in the neighborhood of r, then its value can be dragged from the point p to the point r using the exponential operator. And this can be expanded to the value of this function at the point p plus higher order terms that we don't need because we keep only terms up to second order. And this term here is multiplied by t squared. So if we substitute those two results into this formula here, each term contributes what is shown at each line. This is the first term. That's the second here, and the third. Okay, now let's walk to the point T. So to arrive at the point T, we start from the point P, move along the direction of V up to Q by a parameter T. So this is given by the action of this exponential operator. Then after arriving at the point Q, we move along the W direction by a parameter lambda. So let's consider first this term here, okay, which is this one, f of q is this one. So we expand it in a similar fashion like we did with f of s, and we obtain this expansion here. Then f of q can be expanded in a similar fashion as shown here. WQ of f is expanded by considering the expansion of the derivative around the point P, and we obtain those two terms here. And finally, the second derivative of Q at Q is equal to the second derivative at P plus higher order terms, which we ignore. Then we obtain the analogous expression that we obtained for f of s, but now for f of t. We have those three terms, those three lines, then we ignore terms that are cubic of lambda and t. So if we want to compute the difference of those values, then we see that many cancellations occur. So this one cancels this one, this one, this one cancels that one, and this one cancels that one, and this cancels this. So the only thing that we're left with are those terms here. So if we take t and lambda to have the same value epsilon, then the difference between f of t and f of s to order epsilon squared is given by the value of the action of the commutator v and w on f at the point P. So we see that this walk in those two different directions brought us to two distinct points, S and T, unless the commutator of V and W commute. Therefore, we conclude that coordinate vectors must commute, because when we move along coordinate systems, then we should arrive at the same points. Notice that if we use as function f the function chi mu, then the difference of the coordinates mu of those 2 points is given by the mu component of the commutator v and w in this coordinate system. So if its coordinates are to be the same, then v and w must commute, and their commutator being equal to 0. So let's go on now with the geometric interpretation of the Lie derivative of w with respect to v. Now we will consider a different walk, starting again from the point P in question, but then we move to the right to the point Q by dragging P along V. Then from Q we move to T by dragging Q along W, and then we move from T to S by dragging T in the opposite direction of V. That defines the point S. On the left, we just make one walk where we drag the point P using in the direction of W to the point R. So the Lie derivative of the vector field W with respect to V at the point P is obtained by computing the difference between the pulled back vector W to the point P, that's V star W, and the vector W. This relation means, if we solve for this term, that phi star t of WP acting on any function f is given by the action of WP on f plus t times the Lie derivative of W with respect to V at the point P plus terms of order t squared and higher. But the action of phi star t w p on f is, by definition, the push forward by the inverse function of WP. And by the definition of the push forward, we have here, this is computed by taking the action of W at the point Q on the pullback function phi star f. But this pullback is nothing but the composition of inverse phi t with f. Then we have that this term here is equal to WP acting on F plus T times lambda WP also acting on F. So let me make a correction here. As we know, for any function f, its value at t can be obtained by dragging its value at q with the exponential operator e to the lambda wq. And this will give us this expansion here. Now, if we apply this to the function, which is the composition of phi minus t with f, then we obtain this relation shown here. But let's discuss each term in this equation. The first term here is nothing but the function evaluated at the point S, because this drags t to the point S. Similarly, q is dragged back by phi minus t to the point P. Now, this term will be substituted by this result. That will also put the lead derivative of w with respect to v into the equation. Finally, this term here is obtained this way. We compute the action of w on this function, and then with w of q, this is nothing but the second derivative of this function at the point q. But this function at the point q, for every value of t, is equal to f of p. So this derivative here is nothing but the second derivative of f with respect to lambda at the point P. So, substituting those results, we obtain a relation that gives us the value of the point at the value of the function at the point S to quantities evaluated at the point P. And all these up to cubic order in lambda and t. If we set epsilon to be the same value that we give to lambda and t, then this relation becomes this, and we have terms up to order epsilon squared. On the other hand, f of r can be computed by dragging p to the point r using the exponential operator here. That is equal to f to p, f of p, plus epsilon times the action of w at p on the function f, plus this second derivative term here, plus terms of order epsilon cube. So we subtract those two equations so that we have the difference of the values of the function f at those points, s and r, and we see that the only term that survives to order epsilon square is the value of the action of the lead derivative on the function f at the point P. So let's look at this walk now from the point of view of the point Q. So now consider starting from the point Q, move along W to the point T, and then move along minus V to the point S. Then in order to arrive at the point R, on the left we have to start in the direction of minus V to arrive at the point P, and then move in the direction of W to arrive at the point R. From this perspective, the difference in the values of the function at those two different points is given by the commutator of those vector fields. First, the one that we use to move to the right, which is the vector field W, and then the one we use to move to the left, which is the vector field minus V. So this will give us the value of the commutator of V and W, but at the point Q, not at the point P. But the difference of the value of the commutator acting on F at the point Q compared to the one acting at the point P are terms of order epsilon. So since we keep terms only up to order epsilon square, this difference is negligible. Therefore, we arrive at the result that f of s minus f of r is the value of the commutator V and W at the point P acting on F plus terms of order epsilon Q. By taking this limit of those two equations, we arrive at the equality of the right-hand sides. So when the lead derivative of W acts on any function f, that will be the same as the commutator V and W acting on the function f. This is true for any function f, and we can do the same construction around any point P. Therefore, this relation holds at all points P. And the vector fields on the left-hand side and the right-hand side are equal.